Hello. Oh, that's really loud. 3 classes left. It's a countdown. It's fun. Oh, what a pretty picture. So today and Thursday we'll finish up rotation. Fingers crossed. Like, I'm very optimistic that without going crazy quick, I'll be able to get through what I need to get through. All right, and I say need to. I'm going to call it need to because, again, I need to teach you all about torque and moment of inertia. Because anyone that's mechanical or aerospace, my goodness, you will need that information for future class. Do you have to take statics in aerospace? Yeah. You do? Okay. Yeah. So, I'm just going to assume that's a good chunk of you all. I haven't actually checked kind of the distribution of majors. But yeah, you all need to know what the heck torque is and moment of inertia. So, the good news is we are pretty close to getting that done. I say pretty close to getting that done. We did, so last class, just to give you a recap, we did the rotational variables. Let me just jump to the slide that had, so basically all the kinematics equations had replacements for rotational variables. X became theta. V became omega, which was angular velocity. A became alpha, which is angular acceleration. What's nice is you just put the word kind of angular in front of it, with the exception of angle. And then the other really, really, really nice relationship was to go from one to the other. If you want to go from X or from theta to X, you just multiply by R. If you want to go from alpha to A, you just multiply by R. If you want to go from omega, angular velocity, to velocity, you just multiply by R. So it was really, really nice, straightforward kind of connections. And if you understand kinematics, this isn't too crazy. And then I did do kind of a crazy, then we did do an involved problem where we found the acceleration. I remind you all there's 2 types of acceleration. There's centripetal and tangential, and then that was the whole thing. And then the last thing that we talked about was direction. So we talked about the direction of angular velocity. So just to remind you all, you take your right hand. It's very, very important to use your right hand. That's just how this is defined, whether you like it or not. And you curl your fingers in the direction that it's rotating, and your thumb points in the direction of angular velocity. That's how you find the direction of it. So in this pic, counterclockwise from above, angular velocity is out of the page. Angular acceleration, you find that by saying, am I speeding up or slowing down? If I'm speeding up, it's the same direction as angular velocity. If I'm slowing down, it's the opposite direction. So that was a good time. So much fun. Equations. I think that covers kind of a quick recap of what we did last class. So there, lots of things. So it was a good time. Lots of fun. And then the last thing I left you all with, didn't do this, but have fun with it. Torque. I was actually able to tell you all about torque as well. So that's what we're going to spend today's class on. Hopefully kind of get comfortable with the torque and the relationship between that and angular acceleration. So torque is the reason that things accelerate rotationally. Torque is the reason for angular acceleration. So what I want to kind of before we do anything in class today, what I want to convey to you all is the following. Remember I told you every single variable, every single equation I give you has a linear equivalent. So remember all the kinematics equations, linear and rotational. For torque, what I really, really, really hope that makes sense to you all, that I'm going to do my best to convey to you. So remember F equals ma. We like F equals ma. Hopefully you like F equals ma. F equals ma is great. Really, 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 really useful. Torque is like a force. Torque is like a force, but instead of causing things to go in a straight line, torque causes things to rotate. So we replace F with torque. And then we replace M, and this is what we're going to cover, not probably today too much. Maybe we'll you're going to see it in the lab at least. We call it moment of inertia. We'll get to it. Don't worry. For now, it's like mass. But it's how your mass is distributed around a axis. So we're going to learn about that eventually. But just for now, bookmark that somewhere in your head. And then you all know the relationship between A and rotational. It's alpha. So this is like Newton's second law for rotation. F equals ma. F gets replaced with torque. M gets replaced with I. A gets replaced with alpha. And if you're good with F equals ma, torque equals I alpha is the same exact idea, but for rotation. If you apply a torque, something will either start spinning faster or something will start spinning slower, which totally should make sense. If I push the door, it starts spinning. If you apply torque to a wheel, it starts speeding up its spinning. If you apply, alternatively, it starts slowing down. If you apply a force to something, it speeds up or slows down. If you apply a torque to something, it speeds up or slows down rotationally. Okay? That's the punchline. That's what I need you all to know today. That's what we're going to be kind of practicing, working on, all that kind of stuff. Is that relationship. If you understand F equals ma, I just need your brain to make the connection. This is the same thing, but for rotation. Okay? So I'll do my best. So we did talk about how to find the direction of torque. We did a few examples of this. These are good. We'll just kind of quickly practice these again. There was 2 ways to do this. One, if you can figure out the direction it's going to accelerate, spin your hand in that direction and your thumb points in the direction of torque. That's one way to do it. Find the way that it's going to speed up or slow down. Find the way of angular acceleration, and that's the direction it's going to, the direction of torque. So the first one, it's going to spin faster counterclockwise. So we rotate our fingers counterclockwise. Boom, direction of torque's out of the page. The other way is the swinging door method. I don't know. No one calls it that but me. You put your fingers in the direction of R and you swing it towards F, kind of like a swinging door. So, just practice these real quick. I want to make certain you are decent at this. Sure, the answers are here, but make certain you know how the heck to get these. So, the first one, fingers in the direction of R, we swing it, my thumb points out, fantastic. You all just practice the other two. It's been, a handful of days. This is one of those that you just kind of got to do it. It's kinesthetic, like you got to actually do it with your hand. It may feel silly, but trust me, if you don't practice it, you won't know how to do it on the test. And in physics too, you're going to see everyone during the test doing stupid hand things. It's a thing. So if everyone's doing it, it's not silly, right? So yeah. Second one, which way is it going to accelerate? Clockwise, because the force is, you can hopefully realize that the force is downwards, it's going to accelerate that way. So boom, into the page, but also R cross F, it swings. And the bottom one, it's going to rotate clockwise as well, so it's into the page as well. All right. Great ones to practice. Boop, boop, boop. Okay. And then we talked about this cross product. So a cross product is multiplying the parts of a vector that are perpendicular to each other. The cross product multiplies the part of a vector that are perpendicular to each other. If I have a big old rod that I want to spin around, if I push into the rod or I pull out of the rod, it does not spin. If I push in the direction of R or I push anti-parallel to R, if I push, so remember R points away from the axis. So if I put a force and I pull outwards, it's not going to spin. Hopefully that's kind of obvious. You all know that. If you pull on something, it's not going to spin. If you push on something, it's not going to spin. How do you make it spin? You push down or you push up, which is exactly perpendicular to R. That's what you're doing with the cross product. You're just finding the part that's perfectly perpendicular, which is going to make it rotate. That's all the cross product is there for. All right, cool. It pretty much always turns into RF sine theta. Yay. There he is. Look, next week is today. Yeah, that's us today. Okay. So let's find the torque with this one. And what's fun is you got to use center of mass for this. You don't find the center of mass of the system. You do not find the center of mass of the system. Okay? So let's just talk through this and then you'll see what I mean why I said we have to do center of mass. A horizontal beam of length 3 meters and mass 2 grams has a mass of 1 kilogram and a width 0.2 meters sitting at the end of a beam. What is the torque of the system about the support at the wall? So this is a good foreshadowing of your statics class. This is a system with three-dimensional objects where they are held by a bracket and you don't want them to rotate. You not only want them not to fall, you also don't want the system to rotate. So, first question, where's our axis of rotation? What is this going to want to rotate about? The wall. That's the axis of rotation. You have to define your axis of rotation. If you don't know what you're going to rotate about, you can't do anything. You can't find R if you don't know where the heck you're rotating. So my axis, and you know it tells us, what's my torque about this thing? So that's my axis. Now I'm just going to straight jump to 3. I just told you all the torque is R times F times sine of theta, where theta is the angle between them. R is how far the force is away. F is the force. And sine theta is the angle between those two things. I'll draw R. I'll be very generous. Actually, you all try to draw R. I believe in you. What is the direction of R? Draw it on the picture. Draw the picture. Draw R. I'll confirm whether or not you're right. Don't overthink it. Oh, and sorry, and when I'm saying draw R, draw both R's. Just to maybe make it a little bit more interesting. There's 2 R's you all need to draw here. R is the distance from the axis to where the force is. So ask yourself, where is the force? So, I think I'm seeing a lot of uncertainty. Let's ask the question, what are the forces acting in this problem? Gravity. What's experiencing gravity in this problem? I heard words, but they were just so quiet I couldn't hear them. The small cube, that's one thing. And the beam. Now the question is, where do I draw the force? On this cube, do I draw the force on this right side, on this left side? Where is the force acting on this? If I had to pick one single spot on that cube to say that's where the force is acting on the gravity, where would I put that? The center of mass. That's why center of mass is so useful. This object is semi-complex. I mean, it's a cube. It's not a single dot. But you can pretend like it's a single dot. For the sake of this calculation, that's why center mass is so useful. So we draw an arrow dead center on that guy. Let's call that force 2. I'm just going to pick 2 because it's the one farther away. Great. And then someone said the beam. Where am I going to put the force on the beam? Center of the beam. Force 1. So this is where center of mass is very useful. You can have a really complex object, but if you find the center of mass, you can just pretend like it's all there. And it's really, really convenient. It makes your life easier. Okay. So, if we go back to step 1, you all can find F1 and F2. We know we're finding torque. So what I want you all to do is I want you to find R1. It really doesn't like that spot. And I'll even, I'll point this out to y'all. R1 points, that's R1. And then R2 is that distance. They're vectors. Find the values of F1, F2, R1, R2. And, at this point, what is the torque? Y'all can kind of jump to that too if you want. So step 2 is going to be torque equals question mark. Step 3 is we just gave you the torque equation, RF sine theta. And if you have multiple torques, if you want to find the total torque, the net torque, what do you think you're going to do? Add them together. Quick question for you all. Are these torques in the same direction? Because they are vectors. Are these torques in the same direction or opposite directions? Are they causing the object to accelerate in the same direction, or are they fighting each other? They're in the same. Yeah. Which way does the rod want to move? Down. Which way does the block want to move? Down. Look at that. They both go in the. They're both accelerating in the same direction. The reason I say this is the next step is you're going to add the torques. T net equals torque 1 plus torque 2. But these are vectors. We will have situations where they're fighting each other, and you have to account for that. All right, try it out, y'all. I believe in you. And while you're having fun, let's give you some blinky lights to wake you up. The blinking, it's attendance, but my internet's chugging. So here we are. We made it.
Is it still slow in the building? Is it still slow in the building?
I don't know. Sometimes, it could be my computer, it could be that. It's hard to say. Oh, I forgot to make this announcement to y'all. Student perception of instruction is out. I sent out an announcement about it. You all get absolutely no benefit or fault for filling out that survey. It is completely confidential. You don't get any points for doing it. I don't get the responses until after the exams, all of those things. So I say this as it has zero benefit to you. However, it has a lot of benefit to me for you all to fill that out because it helps me to improve as an instructor. Remember, it's always very useful. Just like it's useful for me to give you all feedback, it's useful for me to get feedback from you all. So I really, 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 really appreciate it if you all fill that out. Be absolutely candid. You can be as blunt as possible. Remember, grades will be submitted before I see the responses. So it's completely anonymous. But even if you're like, man, if I put certain wording in there, maybe he'll figure out who I am. Even if I do, grades are submitted at that point, and I can't change them or anything like that. So there's again, zero risk, but it has great benefit to me. So really, really appreciate it if y'all do that. I think it's only open for 2 weeks from when I sent that announcement was already a couple of days after. So it's not much time. So if you all wouldn't mind doing that at some point, I do read every single one of them. Again, if I want to actually be a better I've told you all, we all make mistakes. There's things I will never be a perfect teacher, but maybe as time goes on, I can get better and better and better. It's one of those limits situations. As time goes on, hopefully I can approach being a better and better and better teacher. Never being perfect because perfection is impossible. But hopefully I can do decent and get better. But I need your help to do so. So anyway, that's my little soapbox. And there's attendance.
If you need attendance, let me know, as always.
They bring in the spheres. Sorted.
Yeah, there's metal balls.
Lots of options.
I don't know. I'm just stupid. Just actually mechanics.
You're like a special graduate.
Yeah.
Which one are you looking at? Oh, is this
It's
mechanics or something?
yeah, someone's in space, you drop a ball here on Earth. And then eventually we're gonna find the deflection, but the first part of the problem is rewriting the omega in
Omega.
the like Earth spin.
Oh.
But writing it in like the Earth's frame of reference coordinates. And I'm just guessing this because it's like write omega in terms of omega and lambda. I don't know.
I'd have to look at it more, and even then, I don't know. All right. Okay, see a couple more phones, so I'll wait a couple more seconds.
Is it like deflection, as in if you drop it, how far does it move from the point?
All right. If you need Leo, he's here. Do I get lucky if I hit this button? All right, try out this problem. The answer will be up there eventually. If you think it's simple, great. Solve the problem and prove that it's simple. See, there you go. It's a confidence booster. Okay. I got 87.22. You let me know. Oh, nope, that's wrong.
Just R1 F1 plus R2.
Yeah, it's just getting the numbers right is the. Yeah. Far away the force is from the axis. So how far away the center is where the force is. And that's what we said. Where if we had to say gravity is affecting that thing, you have to draw an arrow for the force of gravity, where would you draw it? Center mass. So R is going to be how far away from the axis of rotation to that spot. Okay, so I got 57.82. 57.82. Now, what are the units for torque? Great news. They come from the math. It's just, what's the units for R? Meters. What's the unit for force? Newtons. Ta-da, that's the unit for torque. Okay. Now, step one, I can almost guarantee that a lot of people, I don't know what percentage, but enough that it's going to be significant, that got R2 slightly off of what it should be. I don't know. I could be wrong. But it's very subtle. So let's, F1, very straightforward. It's M1 times G. And F2 is M2 times G. Great. Can plug those in. We'll do it at some point. I just don't have room. R1 is very, hopefully, straightforward. It's 1.5. If you look at the picture, R1 is 1.5. R2 is not 3. R2 is not 3. And if you put that R2 as 3, it is incorrect. And I want you all to look at this picture and see why it is not 3.
No.
Look carefully. It's very tiny difference. Again, it's very subtle, but this is where a picture helps you. Where is 3 meters located? At the very end of the rod. Is my force arrow at the very end of the rod?
That could be very.
No, it's very slightly shifted to the left of that. Because it's the center of mass of where this object is. It might seem tiny, but this is the stuff you got to be careful of. It can make a big difference depending on the problem. This one, it doesn't change it that much. But if I made the mass of that block like 20 kilograms, it would matter a lot. So, give you all a few more seconds, see if you can figure out the value before I spoil it for you. So it won't be 3. It's going to be a little bit shy of 3. Minus 0.1, it's 2.9. It's all based on the picture, y'all. The block is 2.2 meters wide. It's very tiny on there, but it's there. If the block is 0.2 meters wide, where's the center of it? 0.1 meters, from the end. So, very, very tiny thing, but it could have actually made a huge difference if that block weighed a lot more. If that block weighed like 10 kilograms, which you may be like, why would a block weigh 10 kilograms? Make it out of steel. Like, it's not hard to make things weigh a lot. It's not hard to make small things weigh a lot. Metal weighs a crap ton. Like, there's a reason everything's made of aluminum. But not everything. Yeah, so anyhow, try it out. Make sure y'all can get the answer. Finish it up now that you got the right number. If you have the wrong number. Y'all get the same answer as me? Cool. It's like I just want to always have someone to double check. I'd look up the answers. So it should be something. And then what's the angle between the R and that? Yep. Side of 90 is 1, which is good. That's good. Because that's just the equation. Yeah, so remember for torque, we want the part of force that is perpendicular to R. And we take the part of force parallel, and nothing happens. Because R is like this way. So if I pull this, does it rotate? If I push this, does it rotate? So which way do I need to push it or pull it? Which is exactly so that's what that sign comes from. It says, hey, find the part of F that is exactly that's what
You don't have to.
I'm stupid. Latitude is an angle, isn't it?
Yeah, this changes. I was just going to say this changes how far out you are.
Great.
So you have to scale it by.
Oh wait, I forgot the latitude.
You have to scale. Wait, X probably scales. Like we can find this, but I want to find. Distance. Because it scales how far up you are on your position. Which isn't a problem because if you do this, you get the theta travel. If you do theta travel times the radius of the Earth, or the radius from the horizontal axis, you get the arc length. Which is because it's just radius from this axis. So you can convert from omega to your distance arc length travel.
the direction of torque is going to come from the picture.
But you need, that gives you a path like this. And you need the displacement from here to here.
Okay, so something that's here that I didn't really talk about. I mean, I have it, but for this specific problem, what is the angle? So the angle is the angle between R and F. So if we look at R, if we kind of extend it a bit, it is this angle. Let's make it purple. And so the question is, what is that angle between R and F? If they're exactly perpendicular from each other. Pi over 2, 90 degrees. The angle is 90 degrees in this problem. Right? Which is good for us. Sine of 90 is 1. That means we're getting the maximum torque possible. It's always finding the component that's perpendicular. If you all can understand that, that's going to really help you a lot. If you understand why the sine of 90 is here. In general, always with physics, sure, you can do the math, but if you don't know why the math is what it is, it's harder to do a good job of it and apply it well. So, but if not, you'll be fine. Okay, so that's 90. So, straightforward, torque net equals M1 times G times R1 plus M2 times G times R2. And then it's just a matter of plugging and chugging. So mass 1 is 2 kilograms, G is 9.8, R is 1.5 plus 1 times 9.8 times 2.9. Of course, I ran out of room. So close. Yeah. Yeah, but I got to fit the 2.9. That's the problem. So let's just snag that over here real quick. Hello, slide. Okay. 2.9 equals 58.92. 57. All right, it'll show up there again. Don't worry. All right, there we go. I made room and I chucked in the 2.9. So all I added was that 2.9 to erase that. There it goes. That's it, y'all. Now my last question to you all that I want you all to spend 20 seconds on. What is the direction of this torque? Great, that's the value of it. The value comes from the math. Direction comes from the picture. We're working with vectors. Remember, vectors, direction, positive and negative, comes from the picture. When it comes to scalars, positive and negative comes from the math. So don't forget that. That's a really good rule of thumb. So yeah, spend a few seconds. You got basically a 50-50 shot. You know what? Let's make it a quicker question. I want to see what you all think. I want to actually see if you are getting it. I could just ask you out loud, and then I could have the 1 or 2 people that have confidence to answer it. What is the direction of torque in the last problem? Out of page, into page. You got a 50-50 shot. There you go. One day the clicker software will open, but for now, think about it. All right. Still loading. Boom. Boom. Don't worry about that one. We'll get to that one. All right, great. Give you all 20 seconds to answer this. I was like, you've had a lot of time to think about it. Hopefully you're confident. All right, 10 more seconds. And 5, 4, 3, 2, 1. Ka-chow. All right, so remember, y'all, 2 ways to do this. You got your rod. Yeah. Ugh. If my hand hits the screen, it goes to the next slide. So you got some forces this way, and the axis of rotation is here. So you know it's going to rotate that. You know it's going to angular accelerate that way. So that's the quick way to do it. Just curl your hand that way to get into the page. That's the quick way. The other way of doing it is R is this way. F is the one that's down. So R points in the direction of the green. Red points in the direction of F. And you do the swinging door and you get the exact same results. Fantastic. Into page, which we did pretty good on. If you missed this, again, just make sure you practice it. I can almost guarantee you a question like this will show up in the final. Direction matters. If you can't find the direction, if you put it as positive when it should be negative or negative when it should be positive, everything turns terrible. Like, we've seen that enough times. Hopefully at this point, it's for you to believe me on that. I don't just do it to make your life miserable. Okay. So let me just show you all this problem. We're not going to solve it yet, but we will solve it eventually. This is what we're going to build to. So I want to show you what I need to teach you by showing you an example of a problem. I have a pulley, and it has a moment of inertia. I haven't taught you what that is, but I will. It's basically how hard it is to accelerate. Remember, mass is how hard it is to accelerate an object linearly. Moment of inertia is how hard it is to accelerate an object rotationally. It's like mass for rotation. The bigger the moment of inertia, the harder it is to angular accelerate that object. Okay, great. It's mounted to a wall. You got some pulleys pulling on it. Let's say against the pulleys. You got some pulleys, you got some masses that are hanging down. And this problem says find the angular acceleration of the pulley. And this problem actually has a few steps in it. You got to use actually like linear forces. You got to draw some free body diagrams. Once you know what to do, it's pretty straightforward. But this is the one we're going to build towards. This is kind of one of the major problems I want us to be able to get to. So we'll get there when we get there. Notice that it's at slide like 27. So let's get there first. Moment of inertia, and I wish we could do angular momentum, but we're not going to have time. We lost a week and a half. Good news. Angular momentum, let me just quickly summarize it real quick. What's the equation for regular momentum? P equals mv, and one day my pen will write and not skip slides. So we replace P with something called L, that's angular momentum. We replace M with moment of inertia, and we replace V with that, and ta-da! And everything you all did for regular momentum, you can do for angular momentum. I won't teach it to you all, but if you can do regular momentum, you can do angular. I would teach it to you all if the hurricane hadn't done terrible things to us. But, we work with what we have, right? So great, we'll get there. So really this slide is on moment of inertia and connecting it to torque. So we're going to talk about moment of inertia. We cannot do the whole connection between torque and angular acceleration until I tell you what the heck moment of inertia is. So we're going to do that today. We're also, it's not written here, we're going to calculate the energy in a rotating object. So, okay. I got this meter stick spinning in place. What's its regular kinetic energy? 0. What's its velocity? Like if you combine the whole system, if you like averaged all the velocities, what's the velocity of the system? 0. It has 0 regular kinetic energy. Does this thing have energy? Yeah, like this thing definitely has energy. How do you know it has energy? You can do stuff with it. Like energy at the end of the day is basically I can do stuff with it. If something has energy, I can convert it to another type. Clearly, if something is spinning, it has energy because if it whacks something, it's going to do something. So I'm going to teach you all how to find the energy of a spinning object. It is not going to be 1/2 mv² because clearly it doesn't work. So that's just foreshadowing. All right. So we'll get to that as well. All right, so here's a really interesting question, which will be your lab today when we get to that. I roll 4 objects down a ramp. A sphere, a hollow cylinder, a solid cylinder, and a hoop. If they all have the same radius and the same mass and the relation to the same height, which will reach the ground first? There is only one right answer. I obviously haven't taught you this, so take a guess. This is a guess problem. Yeah, it's a little unfair, but it's a fun problem. Solid sphere, hollow cylinder, solid cylinder, or a hoop. The hollow cylinder has some internal radius. So a hoop. Okay, well, yeah, you're right. Yeah. Depending on how I define this hollow cylinder, it could have a hollow radius or inner radius.
Oh, okay.
Yeah. Find out. I don't want to spoil it now. Okay, so I'm going to give you all a hint to actually give you a chance of getting it correct. We're going to learn that things are harder to rotate when their mass is farther from the middle. We're going to learn that things are harder to rotate when the mass is farther from the middle. And you may be like, how am I supposed to know that? You know this. If I hold this box of rulers right here, if I hold it here, does it look that challenging? I mean, it's not that heavy. What if I hold it all the way out here? Have you all ever held something really far from your body? It ain't easy. So that's kind of the idea here. When things are farther away, there's some kind of connection there. I mean, granted, that was more of a torque thing, but it gets you the right idea of things that are farther away, you got to get this effect. So what you all need to know is the farther away the mass is, the harder it is to rotate. The farther away the mass is, the harder it is to rotate. So use that logic to figure out which of these will rotate the best. Which one rotates the easiest? All right, 10 more seconds. And 5, 4, 3, 2, 1. Okay, so this is kind of tricky to draw. But if we try to draw these objects, I got a sphere, kind of, sort of. Spheres are really hard to draw. There's some nice shading. Oh, so pretty. Here's a hollow cylinder. Here's a solid cylinder, which looks like the sphere. And then here's the hoop, which is, kind of like the hollow cylinder, but it's lengthwise, it doesn't have a width to it. It's like a hula hoop. So a hoop is like a hula hoop. A hollow cylinder has got some, like a PVC pipe. Okay. So it literally just comes down to which has the mass closest to the center. Whichever one has an average, the mass is closest to the center, that's the one that's going to reach the bottom first. And the answer for that is pretty much what most of y'all put. Highlighter. Oh, can't click it. That's right. All right, it is the sphere. The sphere, if you look at the geometry of a sphere, more of its mass is located towards the middle. I don't have a big sphere. But if you notice, it's pretty obvious that the hoop and the hollow cylinder, all their mass is far away. All their mass is far away. So that's like the worst case scenario. The worst case scenario is a hoop or a hollow cylinder. The solid cylinder and the sphere kind of look the same, but you have to remember that the sphere like bulges out kind of in the middle, and that bulging is some mass that's closer to the middle. So you can kind of think through the logic there. But that's moment of inertia. Moment of inertia is a measure of how the mass is spread out. That's what we're going to be finding. The farther away it is, the harder it is to rotate that object. This is why, if you all ever like riding a bike tire, what's the easiest tires to rotate? Big fat tires or like skinny, thin, tiny tires? Yeah, the skinny, thin ones. If you all ever look at like the people that are doing like super fast fights like in the Olympics, their wheels are actually, the mass is kind of distributed throughout the whole thing for strength purposes and things like that, and they actually like taper the ends in some level. They're trying to keep the mass as close to the axle as possible. Whereas if y'all have ever ridden those bikes that they use at like the beaches with like the giant tires on them, they're super inefficient. They don't dig in the sand as much, which is convenient. It is interesting that a lot of electric bikes tend to opt for those big, fat, wide tires, and I don't know why. But they are more inefficient as far as when you apply torque to them and getting them to.
Because they can have more tread on them.
Yeah, so you do get more traction, which can be safer, I guess, when you're going way faster than someone bicycles normally. Yeah, if you're going, yeah, those electric bikes, they scoot. All right, so there you go. So the farther the mass is, the harder it is to rotate, and the logic here is actually very simple. P equals mv, v equals rw. Just replace v with rw, and you see that to get a change in momentum, if r is bigger, it's harder to get that w. When r is bigger, it's harder to get a bigger change in p. What about torque? So the example I gave with holding out the heavy thing, that one was using gravity. But here's the problem with the wheel, y'all. Gravity is affecting all sides. W here's omega. It was just easier than writing omega. If I have a wheel that's rotating, gravity's pulling all the sides of the wheel. So it's kind of canceling itself out. We'll get to the whole rolling down a hill and why that still works. Okay, so how do we characterize it? All right, let's look through this one step at a time. Anytime I put the entire derivation, do not look at the whole thing as a whole because that's going to be overwhelming. Just focus on the top. Just, you know what? To make it easier to focus on the top, I'm going to switch up things. I'm going to force looking at just the top. I have to fix my stream because it doesn't like that I did that. It really doesn't like that. Okay, maybe I ruined everything. Ta-da! All right. There we go. I'm going to force you to only look at one thing. Hopefully you're really cool with k equals 1/2 mv squared. Kinetic energy is 1/2 mv squared. Nothing crazy. Replace v with omega r. Remember to go from rotational to linear. You just multiply by r. Really straightforward. So v equals r omega, where omega is angular velocity. Great. So you get 1/2 m r squared omega squared. Nothing crazy. This gives the kinetic energy of some mass located at some distance r. Doesn't give you the whole entire object. It just says if I have some mass some r away, rotating at that, woohoo. So if I have many of them, if I have several objects at various r's with various masses, you add all of them together. If you want to get the total, you add them up. Great. Then we're just going to kind of 1/2. We're going to just group those terms together. 1/2 mr squared times omega squared. And then just compare the two, y'all. Kinetic energy was 1/2 mv squared. So remember, v is like w. 1/2 is like 1/2. So this mass is like this term. So we just, ta-da, that's the term. That's where it comes from. It just comes from energy. You just kind of plug in that one relationship. Moment of inertia. Long story short. So long story short, this is moment of inertia. I equals the sum of mr squared. That's it. That is moment of inertia. It is how much mass you have times where it's located squared. And this is both very simple for a single object, but the reality is we're working with three-dimensional objects where r varies across the entirety of the solid. So if you ever have to add up an infinite number of small, tiny masses, guess what you have to do? Yeah, what's a infinite sum of tiny things? An integral. So that is the next slide showing moment of inertia is the sum of mr squared. The reality is you pretty much always have to integrate it to find it for various objects. Now the good news for you all, we're not going to spend too much time on this integration. Like I'll do one example of it, but otherwise I'm going to kind of just give you the moment of inertia for various objects, sphere, cylinder, so on and so forth. There's a big slide with a bunch of them. If you need it, I'll give it to you. So it's like mass. It's like mass, but for rotation. Yeah. The name is not intuitive. Moment of inertia. I have no idea why it is called that. I mean, I've been doing physics so long, it sounds normal to me. I just kind of associate that with rotation, but I recognize that is a bunch of jargony stuff. A moment means something in math and physics. Couldn't tell you exactly what it means. Inertia, is kind of how tricky it is to get something to start moving or stop moving. So it's kind of, yeah. Do you all know what a moment is better than I do? I was like, it's a word that gets used in physics all the time, and I do not actually.
Yeah, I think just like from the definition, the inertia part makes sense. The moment is still unclear.
Yeah, so don't worry about it. All you all need to know is this is mass for a rotating object. This is how hard or difficult it is to get an object to rotate. If it has a higher moment of inertia, you got to work harder to get it to accelerate rotationally. If it's got a lower moment of inertia, it's easier. Remember, it's F equals ma for rotation. This is my m. This is my m for rotation. Analogous to m. I just want to remind you all of that. If you understood F equals ma, a big rocket is hard to accelerate in space. An object with a high moment of inertia is hard to rotate in space. Get rid of every other thing, and that's true. It's hard to accelerate. It's hard to angular accelerate in space. Okay? This is the trickiest thing I have to teach you in rotation. So if you can understand this, the rest is cake. Okay. A 5 kilogram ball is attached to the end of a 2 meter string. If I consider this ball as a point mass and I make the string massless, find the moment of inertia of the system. If you don't have the equation down, Google it. I'll write it up here in a second, needs be, but. So don't worry about the string. In the real world you do, but in this problem you don't. Don't worry that the ball is three-dimensional. Pretend like it's a single dot located 2 meters away. And we spin and spin and spin.
Oh, because it's a point mass.
Yep, that's it. For a single point mass, that's all you got to do. How are we looking? We're looking decent. We're looking good. What do y'all think? How do we get moment of inertia? better. Once you know what the equation is, you have a single object. You know, there's nothing to add. So what's the mass here? I didn't actually see you guys. It's just to get us kind of familiar with the LPA. Fundamentally, moment of inertia is just one squared. It just turns out when you have a solid object, you have an infinite point mass. Oh, you not zero. Okay, technically zero, but then there's no mass here, there's no mass here, there's no mass here. So it ends up that you're not actually adding. You're adding. Yeah, we'll eventually do a lot. And the challenge there is we have to find a way to relate mass to location. If y'all can remember that, that'll be good.
It's not my, like, no.
All right, 10 more seconds.
Oh, that's like
In 5, 4, 3, 2, 1. All right, so we draw a pretty picture because it helps us. We draw our mass out here. We pretend like it's a single dot. There's my lever arm with radius r, my mass here. Moment of inertia is the sum of mr squared. If you only have a single object, you're not summing up anything. So it's just mr squared, which equals 5 times 2 squared, which equals 20. And then you're like, what are these units? Kilograms times meters squared. It's literally the units from the math. What's the unit for mass? Kilogram. What's the unit for R? Meters. And you got to square it. And ta-da. These are really nice units. I say nice. If you know the equation, you can come up with them. You don't have to memorize them. It's not a new name. Okay. Now, this is the easiest case. A single dot. A single point. But let's look at my meter stick. My meter stick is made up of an infinite number of masses, each at a different R. Each located at a different R. So you end up having to integrate that, and I am going to show you all how to do that. We're going to do a linear. We're not going to do it for a sphere or a three-dimensional object because you need what is that called? Triple integrals. If you want to integrate and find the center mass of a three-dimensional object, you got to do three integrals, triple integrals. Technically, you all haven't, the vast majority of you all haven't gotten to Calc 3 yet, so you're spared that. But it's actually not the worst thing in the world. Anywho, here is the center of mass of a variety of objects, and you're like, where do these come from? Integrals. They come from triple integrals. Feel free to check them out in your own time. This is the easiest one, a hoop. This is the easiest one, and we can actually do this integral. I is the integral of mr squared. And actually, let me jump on back to get the actual integration limits. It's r squared dm. Where am I? So zoom back in on this. R squared dm. That's not what I want to do. This one you all can do. You can do this integral. On a hoop, every single point mass is an r distance away. Every single mass is a distance r away. So what does that make r? A constant. If every single point mass is r away, it's a constant. It's just r squared. What's the integral of dm? M. No, so the hoop has mass. Just all the mass is located in r away. It is a hoop with a infinitely thin hoop. Infinitely thin hoop is what this is. You'd be like, what's that? Do those exist? Remember, infinity doesn't exist, but we can approximate things. Approximation is always a handy tool. A hula hoop, depending on your problem, might be able to consider as just mr squared, depending. All right, great. The rest of these, no, I can't do that. The rest of these, I cannot be as kind and just do that. Like this one has a 1/2 term. So if you have a hollow cylinder that we don't approximate as infinitely thin, you got to integrate. That one does end up just being, you can do a one-dimensional, I guess it's two-dimensional integral. If you use cylindrical coordinates, it's, I guess, a 1D integral. I don't think you all have learned. When do you all learn about cylindrical and spherical coordinates? Is that Calc 3 as well? Yeah. Super, super handy. You'll learn about those eventually. They make problems that it would traditionally be really challenging. So like finding the volume of a sphere, doing that in Cartesian coordinates is disgusting. And when I say Cartesian coordinates, that means X, Y, Z. You're going to learn eventually spherical coordinates. You can integrate, instead of X, Y, Z, you can do R, theta, and phi. And they describe any system, whatever. You'll get to it when you get to it. Okay. Oh, fun fact. Let's look at this hoop. The original hoop we did, super simple, right? That's because it was rotating about the center axis there. You have to define your axis of rotation. If I have the exact same hoop, but I instead rotated about this axis like a coin spinning, we have to integrate that. That one is no longer, the R is no longer a constant. You can see R varies based on where you're located. R here being a measure of this. So you can see R here varies based on where you're located. So you get a different moment of inertia. I do not need you all, nor do I expect you all to have these memorized. If you need the moment of inertia for an object, I will give it to you. If I give you a sphere on a test or a quiz or whatever, I will give you that the moment of inertia for a sphere is 2/5 mr squared. Where does that come from? Integration. So I'm just showing you all this to show you that various objects have different moment of inertias. And these moment of inertias, not only do they vary based upon the object, they also vary based upon where it's rotating. If you all look in the bottom left down here, I have I have rods. Every single one, well, let's look at both of these. Both of these are solid rods. One of it is rotating kind of like a hot dog on a, thing at 7-Eleven. And then the other one's rotating like a propeller. Like a what? No one is rotating their hot dog like this. Are they? Maybe they are. Actually, they probably are, actually. You're right. Depends how you skewer your hot dog. And then, we got this crazy one, which is a slab, which I say is crazy. It actually probably wouldn't, it'd be probably fairly unpleasant to integrate. Anywho, I just want you all to see that various objects have different moment of inertias. And I don't know what statics looks like. I don't know how much you're going to have to do this, but you're going to have to consider these various, everything is made of various objects, cylinders, rods, spheres. And so you just kind of break an object into a bunch of simple objects. It's like when they draw a picture of someone, they make the face a sphere and they make the body like a cylinder. If you can do those approximations, that lets you get kind of a good sense of what's going to happen to things. Anywho. Okay, great. These are a bunch of objects. There's a really, really cool theorem, though, that I'm going to show you all that's awesome. And it's super, super handy. It's called the parallel axis theorem. Sounds really fancy, but the name actually makes sense. Parallel axis just means two lines that are parallel to each other. So if I have an object, let's take a cylinder, and I want to find the moment of inertia about a different axis, one that's shifted. So I got a cylinder, my water bottle that's spinning, spinning just like a normal, easy peasy cylinder. What if instead I want to rotate it like about the outside? So it's like doing some weird, almost like a camshaft, I guess, where you got something that's like off center. I think that's what those are called, camshafts. I don't know. Anyway, we're going to rotate this so that this cylinder is instead rotating about this axis that's shifted to its side. So instead of being down the center, it's rotating about this like funky axis. And you're like, oh my gosh, do I have to integrate the whole thing again? No. It's really, really cool. Take the original moment of inertia, just add md squared, where d is how far you shifted your axis. So if you have a parallel axis, if you have an axis of rotation that's parallel but just shifted, just add md squared to the moment of inertia and boom, you got your new moment of inertia and it's great. It's like super, because I remember I told you all these integrals stink. You don't have to integrate again. So let's practice this. I got a sphere. So a sphere rotating about its center is 2/5 mr squared. That's its moment of inertia. That describes how this mass is distributed with respect to radius. What if instead of spinning it about the center, we spin it about the outside? Again, so it's doing this like off-center rotation where it's like rotating about a pole. Again, you can imagine it's like glued to that dotted line and it's rotating about that dotted line. I wish I had a giant ball. Yeah, I could. I should have brought a beach ball or something.
So it's very long.
Yeah, you want to do this demonstrate. So you know, this is a sphere rotating in place. So the one I'm talking about, which is such a pain. Ooh, there's a pole over here. So this problem is rotating about this pole, like around it. It's rotating like around this pole. Anyway. The new moment of inertia is the original plus the mass of the object times how much you shift it squared. That's all you got to do. So try it out. All you got to do is replace it. The original moment of inertia of a sphere, that's the OG, 2/5 mr squared. Then just figure out how much did it get shifted. What is that d? The d is the distance it got shifted, the axis rotation. Alright, so how much did the axis of rotation get shifted? It was about the center, and then it got shifted over here. Close. What's this distance corresponding? The distance the axis got shifted was all this. Just replace d with r and do that. That's it. You all say the axis got shifted. Just replace d with r. Put the OG one in there and add those two terms together. Alright, how much did you all say the axis of rotation got shifted? I haven't hit the button yet. No, no, you can't actually answer it. Boop. Alright, so y'all tell me how much did it get shifted by? Yep, so you just replace d with r and then do that. Alright. What she told you. No. Okay. You all get his final answer. Alright, what y'all say? This is the axis of rotation. And it gets shifted over here with the axis of rotation. That is the number. So how much was the shift? How much did the axis of rotation get shifted? Yeah, so is it half r or the full radius? The full radius. So you should place d with the full radius. R. Plug in stuff in calculation. Plug in the original moment of inertia about the center. Where d is y'all figure it out? How much did it get shifted by? Because, yeah, what is d equal in that case? Yeah. It got shifted by the full radius. Cool. All right. 10 more seconds. I think we've gone around to everyone. All right, we'll close this out in 5, 4, 3, 2, and 1. Boop. So I think you all, like, we went around and I think we checked with you all. If my original was through the center, how much is my distance? It got shifted by R. So yeah, you just take your original, 2/5 mr squared, and you just add the new one, mr squared. Woohoo. And that comes out to 7/5 mr squared. Yay. Okay, there's one last equation I want to show you all. We'll do this moment of inertia. We'll practice this again next time, but since we're running out of time for the lab, I'm going to scroll because I need to teach you all this very, very briefly. You've actually already seen it. The kinetic rotation energy is 1/2 I omega squared. We derived that actually previously to get I. So remember, y'all, K is 1/2 mv squared. And now we have two different kinetic energies, y'all. We have a linear, let's call it translational, kinetic energy, and we have a rotational. And they look very similar because I just replaces m, and angular velocity just replaces velocity. And this is the equation that tells you how much energy is stored in a rotating object. The bigger the moment of inertia, the more energy is stored. The faster it's spinning, the more energy is stored. Just like regular kinetic energy. The more mass you have, the more kinetic energy. The faster it's moving, the more kinetic energy. If it's not rotating, this term is 0, which is why you haven't cared about it up to this point. You all haven't been worried about this because we haven't been dealing with rotating objects. But for our lab today, you will be. So we need to consider this. One thing I'm slightly concerned with is these ramps are fairly smooth. So they're going to slide out the wazoo. Will they even roll or will they just slide? It's fine. It's fine. The wind ramps are better, but, you know, all part of the process. Yeah. Yeah, we're going to see how this one goes. The first part, no problem. All right. So at this point, y'all, take a breather. We'll make sure to have some time. So next class, we'll hopefully be able to finish everything. I'm pretty optimistic at this point. Moment of inertia, I got through most of it. So at this point, it's just practicing torque and moment of inertia, and we should have plenty of time. And that still leaves Tuesday to review everything. So I'm not covering up new content until literally the last day. We're doing it till this Thursday, and then Tuesday is a review day on everything. And by review, it's just going to be me like pulling up the slides from test 1 review, test 2 review, reminding you all of all the things that we've been using this entire time, and then doing some random practice problems to make certain you all didn't forget things from test 1. So, there we go. Take a breather. You got take 5. We'll resume in like 9:22. Okay. So yeah, check out the lab because show you all this stuff before things get worse. It should be in web courses. I'm fairly confident. I posted it there as well.
Do you want to check that the grading is set to groups?
Yeah, I'll double check that as well. Oh, it's still going.
The one on campus is set up what you sent us, right?
I'm hoping so. No.
It just, you have K translational equals 1/2 omega squared. It just needs to be rotational.
Oh, goodness. Is the assignment open? Do I have time? No, it opened. Okay, no one can access it. Yeah, that's fine. They can see all my things. The stream's also going on.
don't know if the meter stick. Okay, yeah.
I need to play this. So I have this weird triangle, which technically across this point. 290. I have this. This is no. This is no.
You will need a ramp, and at some point you will need a sphere and a something that's not a sphere. You definitely need a sphere, though. Well, we'll get to that.
Tuesday I had to be here at 8.
For now, make sure you're in a lab group.
Yeah.
We're doing it differently, but
Yeah, I'm doing it probably not the more efficient.
yeah.
I'm doing it.
Yo. Oh no, no, you don't want to do it. That's all right. You can. There's a. Do you all have a third person?
I submitted this.
You have two? Logan, join them. They're great.
Well, I'm not too concerned right now because we do like problem solving.
Not really. Oh, and technically you don't really need a meter stick because the ramps have meter sticks on them. No, you're welcome to grab a meter stick if you so desire. They are fun to kind of wave around and
I guess I'm
stuff, but.
It's a project. Also, if you've been doubting if you should be a physics major, I think this is.
And then reminder, whenever we set this up, we'll have the ramps on the table so that Leo, Angelina, and I don't end up tripping and die. Yep. Yeah. So just be prepared for that. Like right now, yeah, sure, lean them against stuff, but just when you all set them up, that's just a safety reminder. Have the ramps on the tables. Make certain you have some space available for that because otherwise they're a tripping hazard from here for others. All right, how's our assignments going? How's our lab group allocations? 36 people are still not divvied up. There you are. You can see yourself. You're on the big screen. And then objects-wise, you only need one sphere and then something else. I don't care if that thing's a cylinder, a hollow cylinder, don't care. I guess a hollow cylinder might be better. I'm not sure. Oh, Leo, do you mind going down to the demo room? We need calipers. They have a box of them that is located like that initial hallway when you walk in. They'll be on the back right. They're not sure where they are. Philip knows where they are. Yeah. They're gonna need calipers for this. Yeah. All right, and once you have your group members, you can open up the lab and start reading through it. And the first thing is, how can I design an experiment using sphere cylinders to be able to find the moment of inertia of an object by simply rolling it down an inclined plane? How can I find the moment of inertia with a ramp, cylinders, and your smartphone? At some point, we will need to measure the masses. You will need that eventually. We'll put scales on at some point. Just make certain you have a sphere. Every group needs one sphere. If you don't have a sphere, the second part references a sphere and you'll be confused. Scales aren't on. They're under there, which is where everything else is, so we'll get them out in a second.
There's no one in there for me to ask.
Ah,
And I walked down a couple hallways.
I know where they are.
Sorry.
No, you're fine. That room's like.
I'll just get standard.
Are you considered a friend? Huh? Are you considered a friend? Oh, man. All right. Oops, sorry about that. Okay. While we're doing this, go ahead and do attendance before I forget to do that. And again, do not start taking any. You can measure the mass of things. That's fine. Do not start doing tracker data until we walk through the procedure. Start coming up with your procedure yourself, but do not start revealing any data because I don't want you to collect bad data because you jumped the gun. But do come up with your procedure. Come up with the procedure. Do not skip that box. How the heck are you going to actually do this experiment? Think about it yourself. How can I find the moment of inertia with only a scale and rotating an object down a thing? Rolling an object down a crazy surface. You kind of come up by weird shapes. Like a weird thing. Just like didn't have a nice moment of inertia.
I have a question.
Could it show the purpose of it?
So my group member is asking me to ask you a question for him. He's 10 minutes away and wants to know.
Yeah.
There is?
Yeah, 10 minutes. He's not going to miss that much alive. Just have him come in and do it. He'll need to join another group, though.
Yeah, that's
Because your group's full. All right, make sure you do attendance because it's going to disappear. Leo's got you at some point. Right now, he's got you. If you need to do attendance stuff, go up to Leo.
Really?
Yeah. No.
Like the first one.
All right, you all got like 30 more seconds to come up with a procedure. It's a puzzle. Don't wait for me to give you the solution to it. That's boring. Yeah, it's not
Oh,
fun.
you're here for attendance. I'm sorry. That's my bad.
It's a really simple puzzle. That's why it's good. Where I kind of like outline how to do it before. Why do you have eraser on it?
I mean, it's not a...
Oh, okay. As long as you zero it out, that's fine.
So I'm just gonna.
Yeah, that's fine. It's okay.
That's
That's.
smart.
I just want to make. Yeah. That is as long as you are subtracting the eraser.
Yeah.
This is the line for the scale.
All right.
Is that yours? Or? No.
So let's talk this through, y'all. Again, if you read the outline in the beginning, it kind of walks you through it. Part A is going to be very straightforward. Part B, I got to explain some more for y'all. All right, so Part A. If you all just read the beginning, it told you kind of how you're going to do it if you just kind of recognize the equations. Conservation of energy. Conservation of energy. If you all check out this equation, what energy does your thing start with at the top of the ramp? Potential, yay! We know it. What energy will it have at the bottom of the ramp? Kinetic, but what kind of kinetic? Translational and rotational. It will both be moving and rotating. So you get this equation. So this equation says if I know how high I start and I know how fast I'm going, I can find the moment of inertia. Okay? I guess you do need to know the radius of your object as well. All right. Which somewhat defeats the purpose. Anywho. Oh, that's a good question. I have no idea. Gosh, I don't want the number to be accurate. I'll figure it out in a second. I'll figure it out. All right. So, part A is really straightforward. Tracker. You're going to record it. Now, notice I put in all bold, all caps. In tracker, make certain you set a coordinate axis that's parallel to the ramp surface. Why? You need to measure its velocity at the bottom. You don't want its x velocity. You don't want its y velocity. You just want its total velocity. If your coordinate axis is not, let me draw a picture of this. Show you all what I mean. If you all, in tracker, this is why I told you, do not collect data until I start. Here's your ramp. If you all set your coordinate axis like this nice purple line, and you say, oh, I'm going to take the velocity as Vx. That is not the velocity of your object. That is the velocity of your object at the bottom this way. So what do? Rotate that coordinate axis so that the velocity will actually, you can actually just get the velocity straight from the x component. Okay? If you do not rotate it, your data will look, either you'll have to do an extra step or you'll just get it wrong. If your coordinate axis in tracker is this, and you want to find the velocity in this direction, guess what you're going to have to do? Vectors. How do I find the net if I have x and y? Doesn't that seem like a fun extra step that you could avoid? Yeah. There's probably, there probably is a way to automate it in track. All right. Do note, though, last thing I want to mention to you all. Actually, there's lots of things. Great. You all said it like this. Will this tell you how high up your thing starts? No. You need to measure before you all record stuff. So actually, you might need a meter stick. I lied. You all need to record the height. And one more thing you need to figure out, the angle. You will need that eventually. For now, trust me. I'm going to let you figure out how to find the angle. I believe in you. All right. Last thing. Actually, two more things. I have you all doing it for a sphere and hollow cylinder. Just do it for the sphere. I've changed my mind. Why am I having you do it just for the sphere? If you do it for both objects, one, it takes more time. Two, they're going to have different heights because they're going to be one behind the other, and then you have to measure that, and then that's just going to result in complications. So great news. Don't worry about the hollow cylinder. We're only worried about spheres this wonderful day. Okay. A few more things, y'all. I know lots of instructions today, but if you miss these, I'm going to end up with a million questions, so I'm trying to catch them. At some point, you are actually going to find the actual moment of inertia. You need to find the radius. How are you going to do that? We have calipers. You can either use a caliper, or someone in the demo room had a really great idea. Measuring the radius of a sphere is actually kind of tricky if your calipers aren't big enough. I need one of those chonky spheres. Chonkier than that one. Where's that big blue chunky sphere? All right. Okay, here's the problem, y'all. My calipers don't reach all the way down. They get close. So someone had a really good idea. If you take two parallel surfaces, this is actually how you do this most often when you're machining things. You can use a caliper, or if you get two parallel surfaces, i.e. like two books, put two books here and then just measure the distance between the books. It's a kind of a clever way of finding if you have a really crazy shape and your calipers don't quite reach all the way down. Two parallel surfaces, measure the distance between the two parallel surfaces. That gets you the diameter. All right. For part two, the whole purpose of the second one, and you're going to need to kind of look through these equations and make sense of them. You all can do this. The acceleration of an object going down an inclined plane is less than an object sliding down an inclined plane. And the purpose of the second part of the lab is to show you that. If you have a box, ironically, a box sliding down a frictionless plane will go much faster than an object rotating down a friction plane. The key part here is you need a frictionless plane for the first thing. So, anyway, this first one, in terms of the kinematic equation for just an object sliding down, and then it does some various derivations. Check it out, think through it. You all can look through it. Like I have the utmost confidence you all can make sense of this, so I'm not going to spend too much time. This is just the linear motion of an object on an inclined plane. We did this a bunch. So make sure that makes sense. Torque equals I alpha. That's something I mentioned to you all. Torque equals RF sine theta. What is the force that makes an object rotate down an inclined plane? It's actually friction. If there's no friction, there's no reason for something to roll. It'll just slide. So friction is actually the force responsible for an object spinning down an inclined plane. No friction, no spinning. All right, great. So you set these two things equal to each other. And then you're like, what do I do there? Remember, y'all, that A equals R times alpha. So you can replace A with R times alpha, make the substitution, and then it just asks you to do a bunch of things. All right? This is all just a derived thing, so you actually know what you're actually doing. I believe in you. Long story short, y'all, take a video of a sphere going down it, measure the height, measure the angle, answer the questions, and it'll all work out fine.
Also, okay. So, quick advice, use a low incline, because if it goes too fast, it'll be difficult to see the rolling motion.
Yeah, if you go too fast, it'll actually start slipping and it all falls apart.
And we
You don't
are
split.
we supposed to not use the cylinder at all?
Without actually rolling.
No, so you do it for both the
Oh, and
sliders
right,
and
out on the ground.
yeah. So if you look on the table, it says you want to measure the velocity.
Okay.
Yeah.
And then see if you can find your switch for both. Okay.
Yeah.
Yeah, let's go.
These scales do not measure the mass of
Yeah,
this.
I went over to the they don't like.
They don't have a scale.
Too heavy.
Yeah, that's one of the things we want to. Yeah, it's too heavy. So I don't know if there's a creative way.
There's a little. So
I mean,
spheres,
we
but
could
they're
put some masses on here. On the. I don't know how jank that is.
yeah.
Like, my assumption is. No, this arm is too
Because
big.
what's the max this goes to? What is it?
610.
It's such a weird number. I would just assume it's a 1 kilogram ball, right? Like,
That'd be great, right? I think it's too. Yeah,
it's
that's,
like there's
it's
no
at
way
least-
that it's not. Like, it's a solid.
it's definitely more than a pound. Yeah, that's fine. We got more spheres probably somewhere. Assorted balls.
Yeah.
So
Well,
if need be, they can do a bouncy ball.
There's the little ones. That they're
Do we have? Is there a scale in the double room that we can measure one and count what it is?
They're all these crappy analog scales.
They have
Analog is not better.
They have like the big one that like is for people.
Those tend to not be as precise.
Especially for something that's small. I'm confident that was a program, but
Just say
it's my intuition. It's not science,
I mean,
so.
if we say it's a kilogram. Wait.
No, because they're finding moment of inertia. It's a massive part of it.
In the full energy equation, it's mgy plus 1 mg squared plus 1 half I.
Omega squared.
How was it?
I has
But I
said
is not
I put it.
exactly.
I did 25.
I did like 23 and a half
23 and a half.
because it was being sticky, so it like landed kind of at 30, and then I was like, yeah, it's fine.
Yeah,
23 and a half.
whatever. I'm just gonna say that.
Yeah, we'll see how this goes.
Yeah.
I think this live's fine, but I'm not sure. But I couldn't think of what to do. Like that was a bad thing. Hello. All right, you just need to find a group of 2. Join their group. Hop in. No one's gotten too far. All right, and I see a lot of random support. Just make certain you all, after you get your video, immediately remove it from the floor so I don't trip or anyone else trips. Safety first. I don't want to be liable for anyone hurting themselves, including myself.
Then they get to sue their phone.
Oh, and this is our last lab, y'all, so treasure it. Yeah, no more labs after this, so, you know.
We don't know.
Yeah, so in an ideal world, I'd have 11 labs, I guess. 10's a nice round number, though. I'd say ideal world, meaning if we hadn't missed a week, that's kind of what it would have been. Well, is that the case? Yes. Yeah.
Because then you'd have the Thursday for the review anyway.
Yeah, I would have had. Oh, I can close this now. Yeah, so we're gonna see. I mean, I did the